Shall we start? Well, I think that we can start our afternoon session. The order is kind of peculiar. We should have probably have presentations of experimental work and measurements first. Somehow we put them the other way around. So tomorrow morning you will mostly listen about measurements, how data were taken, and today you'll see what we did with data in our models. But I don't think it matters much. So the first presentation is on how we got the data and we had to prepare them for models. And this is some kind of review of data that were taken and how they were essentially prepared for models in general. And then we'll talk about 1D models and then 3D models. Then the data needed additional processing for 1D model, for example, etc. Let's start with this. I'm the one above, and Spasojevic Budinski is sitting there and operating this whole thing. Let's go. This is the area we're working on. Between Bezdan down there, Mohac up there, so Mohac to Bezdan is the flow direction. It's about those, as we said, 24 kilometers or so. We choose the mid-section of 6 kilometers to put those 7 cross sections with, I'll call them data ranges, where we're taking detailed data, flow, sediment, etc. And for the whole sector, we had bathymetry, detailed bathymetry data taken, and we were also relying on some data from Mohac and Bezdan hydromet stations in Serbia and Hungary. Next one shows, first, I put it first because we cannot start any modeling without bathymetry. So this is bathymetry data, some detail here. Let's call them cross sections, but they're not, straight line cross sections, but kind of cross sections about 100 meters apart. We were able from that, it's pretty, this part here is not exactly 100 meters apart, which was the first data set. There was some misunderstanding whether it's 100, 200, etc., which was corrected in a second data set. So we essentially have cross-section data, bathymetry data at the frequency of about 100 meters, measurements 100 meters apart. That's good enough for us to use some tool like GIS, put it together, build a 3D model of a riverbed, and then we can use it for whatever, to cut cross-sections for 1D model, to build select the mid part for 2D and 3D models, etc. Now, this central part, since we did it in a democratic way, that's about 24 kilometers of sector. It's about 1/3 in Serbia and 2/3 in Hungary. Then we selected the central part with detailed data to be about 2/3 in Hungary, 1/3 in Serbia. These are our selected data ranges. This is upstream end of that area. This is downstream end. Border is somewhere in between these two. So there are 2 of them in Serbia and whatever, 5 of them up there. Our way that we are showing them and presenting them here on this picture, and later on when we present the data, is that those are names that we will be using when we present the results, and what was measured in each data range was, it has 7 data verticals, let's call them that. They are numbered here from 1 to 7, starting from the left bank. All 7 data verticals were used to measure velocity distribution along the depth, and 5 of those 7, those inside ones, so called, it's 2 to 6 here, were used to collect sediment data and other constituent data, chemical, biological. The chemical, biological part was reduced a bit to 3 verticals in the second set of measurements, but in the first one it was 5 of them. So that's our way of presenting them, and that's how the results will be presented. You can see the detail here, let's say 7th range, which is verticals 7.1, 7.2, 7, etc. to 7.7. Where were we? On the first strip, Mohač is where?
More upstream.
Much upstream.
Upstream from the range 1?
Yes.
Okay, and then we were at Pickett's, which was somewhere between the two.
Downstream.
More downstream even, okay. Besides that, okay, we can go on. Besides that, there were measurements of, while bathymetry measurements were taken, there were also measurements of free surface elevation at each, no, this is discharge, sorry. At those 7 data ranges, discharges were measured also using ADCP. Typically 4 crossings. Let's look at the first one. Typically 4 crossings. These are dates, time of each crossing, approximate time, because one crossing takes what, a few minutes, 10 minutes. And then we extracted from those 4 measurements average discharge, and we also extracted the average time for that discharge. Why? Because we had essentially unsteady, not too unsteady flow, too much unsteady, but still unsteady flow, because you'll see later on that discharge at Mohač, for example, over those 5 days of measurements was changing for about 100 cubic feet per second. It was around 1600, but it went from 1650 to 1550, something like that. And then at the downstream end, Bezdan elevation data showed that elevation was changing for about 30 centimeters. Not extremely unsteady, but still unsteady flow. So we put models together as unsteady flow models, and then we needed exact times of measurements to compare our results at that time with measurements that were taken at the same or approximately same time. While bathymetry was, measurements were taken, there were also measurements of free surface elevation at roughly each round kilometer, plus Bezdan, which is 1425.5, plus Mohač, which is 1457, almost 56.9. And also we needed time for each of those free surface elevation measurements, again, to be able to compare it with unsteady flow and unsteady flow simulations with models. These are results of ADCP velocity measurements. What we can see is that vertical velocity component, this is in a general coordinate system. So east, west, and north, south are our U and V velocity components. W is vertical velocity component, which is almost 0 in most cases. We can go through all of them. Nothing much is happening. Some of the, if we go previous, in some cases, previous slide, in some cases, if the depth was small, we have less than in others, but that's pretty much going. Pretty much the same thing. Okay. Sediment samples were processed to obtain grain sizes, grain size distributions, and for both suspended and bed sediment samples. And for suspended sediment samples, we also had the suspended sediment concentration. Now these are suspended sediment samples, and now I call this sieve diameters, but I'm not sure that suspended sediment sieves were used for suspended sediment, so it's probably based on fall velocity.
Yes, the settling velocity.
Settling velocity, fall velocity approach. Which means that these are, I mean, does that mean now that the question here, when we look at the bed material, then we have sieve sizes, sieve diameters, and then what's in between is represented by representative grain size diameters, which is in between the two. We use the geometric mean usual approach. Is this correct thing? Is this between those two, or is this related exactly to those numbers? Because those are not sieves. So diameter for suspended sediment, that's defined by settling velocity.
Yes.
Is exactly not the, this is not the range. This is the value, or is it the range as we presented it here?
I don't understand the question. But the settling times are defined by diameter classes. There are settling times for each range, actually.
Mm-hmm.
That means that in between these two diameters, it is settling during a certain time period. Then it is the tap is closed, and then from the next fraction is emptied during the next time period. So that means that we...
So it still represents the fraction, as
yes,
we put it here.
Yes,
okay.
yes.
So it's in between those two sizes,
yes.
The representative grain diameter is...
Yes, it is.
Okay, okay. I wasn't sure if we can go. We also had concentrations, which we'll show a little later, besides the grain size analysis. And from that concentration and grain sizes, for those fractions that we defined over there, we can find the suspended sediment concentration by size class, which is what's plotted here. We have, if we go to previous slide, we have, let's see, 1, 2, 3, 4, 5, 6, 7, 8 over there, and we can see that not all of them were found in suspension, because for some of them the fraction was 0. So we have 6 typically of those 8 that the previous analysis shows, and their distribution over the depth, because we had typically 5 samples over the depth, so we can, for each grain size, we can obtain the distribution, corresponding concentration distribution over the depth. Why do we need that? Because all our models are including sediment size fractions. For modeling each sediment size fraction separately, I said to myself last time after the opening conference presentation, I said to myself, I'm not going to show a single equation this time, since I've been showing all those equations and I got some being criticized after that. But I will remind you that in those equations, it was told, I said that last time, that we are modeling each sediment size class separately, which means that in suspension we are following each of those as they travel, and on the bed we also model the change in size fraction distribution of bed material. In our equation or equations or general equations of those type, they're called beta, Greek beta size fraction, which is not percentage, which is a fraction. So if something makes 50% of material at the bed, certain size class, then size fraction is 0.5. You can go ahead. It's fine material. So typical distributions are these, more or less constant over the depth, except that we have some cases like this one, or some peaks here and there, which are most likely, I was meeting those, seeing those things before, most likely attributed to eddies in a flow, which occasionally add more into our sampling bottle or whatever, and the sampling bottles in this case are 5 liters, right? Yeah, so 5 liters is still not enough to make something more average. It's still prone to sudden additions through eddies, etc. Forrest Holly once told me that, are you sure it's eddies? Are you sure it's not the catfish with her tail splashing in front of a sampling bottle? Go ahead. So that's pretty much it. The same thing, same picture. We have this one, which we didn't finish cleaning up with the measurement team. Range 5 has only one vertical, so I'm not sure why. Go on. These are verticals in range 6 and range 7, and that's what we extracted, except for, I'll show concentrations in a minute, what we extracted from suspended sediment data, and then from bed sediment data. Those are the fractions. Now this is sieve, right?
Yes, it is.
For sure. And those are average diameters, again, geometric mean. And if we now look at the samples, give me the previous one. The first, again, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 of them. Some of those coarse ones are not appearing at all in samples. So when we look at the distribution, we can see not only that some of those the coarsest ones are not appearing in distribution. We see that we actually have something like a 3 dominant size classes at the bed surface. On these only 2, but you see there's on those others there is 2 or 3 dominant ones. Have cases like this with some others with small amount, 1 sample, etc. Go ahead. Yeah. And that's about it. We don't have suspended sediment concentrations here, right? No. So this is just the presentation of data, what was measured, and what how we prepared them generally for models. So now I ask myself, do I need break? And I don't, so we can go with the next one, which is first step in modeling. Now we use those for